Yeah, we're on 78, 78. Okay. Hopefully, you all know that we have a quiz coming up on metric conversions on Wednesday, and we have the test on Unit 2 the following Tuesday. Okay, so we got a quiz Wednesday, and then the test the following Tuesday. That should allow you to get everything back and whatnot and stuff. Okay? So, the only thing we haven't done with metric conversions is the ones where we have this little slash Dewey, this over that. Now remember, every time you see it in this notation, you should rewrite it as 352 megagrams over kiloliters, and you should write this one as nanograms over centimeters cubed. And it is expected that you memorize that 1 milliliter is 1 centimeter cubed. And if you're like, where are we? We are on page 78. I'm going to show this all in one line to start with, and then we will quickly go through how to do it using the convert the top, convert the bottom, then divide. Okay? Now, going from megagrams to nanograms, let's remind ourselves that if we have a prefix unit and we have another prefix unit, what do we have to go through in the middle? We have to go through the plain unit. Okay, so in this case, we would be going from megagrams, which is the prefix unit, to plain unit. Plain unit would be the gram, and the prefix unit would be the nanograms. So we're going to go from megagrams to grams to nanograms. And then the bottom part we're going to convert. Kiloliters would be our prefix unit. Our plain unit would be the liter. And then our prefix unit, well, we want centimeters cubed, but we know that centimeters cubed and milliliters are the same. So we can then convert to milliliters, and then we can take our final step to centimeters cubed. So we're going to go from kiloliters to liters to milliliters, and then we can just do a simple substitution. We don't even have to do a conversion for that last one, okay? So let's take a look at what this would all look like in one line. We want to find the number of nanograms per centimeter cubed, and we are starting with 352 megagrams per kiloliter. I'm going to convert the top part first. So let's convert our megagrams into grams. So we want to cancel our megagrams. It has to go on the bottom, and grams have to go on the top. Mega means 10 to the, tell your partner, 10 to the 6, okay? And does the 10 to the 6 go on with the gram, or does the 10 to the 6 go with the megagram? It goes with the gram, because what goes with the prefix? The 1 goes with the prefix. Okay, the 1 goes with the prefix, the 1 goes with the prefix, the 1 goes with the prefix, the 1 goes with the prefix. I appreciate that. You get an A+, sir. All right. Now, we need to now convert from grams into nanograms, so we need to cancel the grams. They are on the top, so they need to go on the bottom, and we need nanograms on the top. Nano means 10 to the, tell your partner, -9. Okay, and that goes, the 1 goes with the prefix, and the 10 to the -9 goes with the gram. We've now got nanograms on the top, which is what we wanted, so we're just going to stop converting the top part. But what we do have now is we have kiloliters on the bottom, and we don't want kiloliters. We want to convert to liters. That means our kiloliters have to go, do kiloliters go top or bottom? Top, because they need to cancel out and they are already on the bottom. So kiloliters on the top, liters on the bottom. Kilo is 10 to the 3. Okay, so we have, where does the 10 to the 3 go? With the kiloliter or with the liter? The 10 to the 3 goes with the? Yes? Goes with the liter. 10 to the 3 goes with the liter because the 1 goes with the prefix. Oh my God, okay. And keeping going, that gets rid of our kiloliters. Now we need to cancel our liters and find the milliliters. So that is, milli means 10 to the -3. And if you have trouble with this, just when you're writing the quiz, just at the very beginning, you're going to be like, okay, mega, kilo, deci, centi, milli, micro, nano, 631,236, 9 is for the nano. Okay, and then you'd be like positive, positive, negative, 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 okay? And then you put a 10 beside them. All right, so milli means 10 to the -3. So we have 10 to the -3 milliliters per liter. I like that look you're giving me. No, I'm just waiting for people to get like mad at me for doing it wrong. Yeah, Miss Vance, come on, get with it. What do I need to switch? The 1 and the 10 to the -3 because the 1 has to go with the prefix. Oh my gosh, there it is. The 1 goes with the prefix. All right, and then that's going to be a 10 to the -3. Now, you have a choice as to how to calculate this. You can do it on your calculator. Everyone grab your calculator. Okay, so we're going to start by having our 10 to the 6. So we're going to multiply by 1 times 10 to the 6. We do not need to multiply by 1. There's no point in multiplying by 1. What we do want to do, though, is we want to divide by 10 to the -9. So that's going to be 1 times 10 to the, I'll use the other option here, -9. So we're dividing by 1 times 10 to the -9. And then we're going to divide by, I'm running out of room here, so I'm going to put it on the next line. 1 times 10 to the 3. And then we're going to, what are we going to do with our 10 to the -3? Are we going to divide or multiply there? We're going to multiply by 1 times 10 to the, negative 3. Okay, there we go. Negative 3. Why does it do that sometimes? That's weird. Okay, there we go. All right, you throw that all in there and you should get 3.52 times 10 to the, and I'll let you tell your partner first before I tell you. $3.52 times 10 to the, you should get 11. Hopefully, fingers crossed. If you didn't get 11, come talk to me after class about your calculator, okay? The other way to do it, if you don't like the calculator, no calculator, is you can say, I have 352 times 10 to the 6. And now I'm just going to say all the rest of my things are tens, yes? And I'm dividing by 10 to the negative 9, so I'm going to subtract negative 9. And then I am dividing by 10 to the 3, so I'm going to subtract 3. And then I am multiplying by 10 to the negative 3, so I'm going to add negative 3. So we've got 6 plus 9, that's 15. 15 minus 3 is 12. 12 minus 3 is 9. So we have 352 times 10 to the 9, and we never leave anything in no-no notation. We always change it into scientific notation. So that would become 3.52. That got smaller, so the 10 to the 9 has to get 2 places bigger, 10 to the 11. Would that be a perfectly good answer, or am I missing something? Yes. I'm missing my units, so I would need to go back and say, what the heck are my units? Ooh, look, I have milliliters, but I know that those are centimeters cubed, and that's what I wanted. So centimeters cubed are going to be on the bottom. And what do I have on the top? I have nanograms on the top, so that is nanograms per centimeter cubed. Okay? And Hebden? Page 17. Number, is it page 17 or is it page 21? Number
Page 21, number
Page 21, number 17. Page 21, number 17, L to the end. Okay, that's to prepare you for your quiz on Wednesday. And if you did not previously do page 21, number 17, A through K on the weekend, that was your homework on the weekend, then you need to do those as well to prepare for your quiz Wednesday. There are also extra practice stuff in 2.4E. You can be like, oh, I would like a whole bunch of metric practice. Oh, there's rate conversions in here. Why am I bothering with Hebden? You know, you could go through here and just do them on here. Yes? So 2.4E is also a good choice. Your choice. And or 2.4E. Yes?
Is it page 21?
Huh?
Yeah, page 21 on Hebden.
Page 21 in Hebden. So that's in on our teams. We go to our general and we go to files, or you sign out a book. Yes? Huh? James Hebden, he was a chemistry teacher from Kamloops. Yes, Kamloops. And he wrote a book. And here it is. Okay? And you go Hebden, and then it's in there. Okay? Or you can sign out a book. I think so, but I don't know for sure. There was another guy who did these fabulous like worksheets and stuff, and he used to have this website, but it is no more. So I'm wondering if he is no more. I don't know. Anywho, that's it for that. Today we are going to spend the rest of the class talking about the lab. You will need some paper. So go get yourself some paper. If we run out of paper at the back, let me know. I can get more.
Someone left their quiz in the paper bin.
Oh, okay. That's nice. Hi.
So confusing, but I can get it. So I'm so bad. I can understand. Can I see my last quizzes that I made? The test and the quiz.
Yes. Ella, I have one more quiz for you.
This is the test, right?
Huh?
This is the test, right?
That's quiz.
Quiz?
Quiz.
Okay.
I can't show you your test right now because that would require me going and finding all the tests and sorting through them. Yes. Yes. 466. Yes.
I thought $1 beating that.
You could argue that.
Or is it like because I guess
You could argue it. I'll give you the point. It's fine.
And then, like,
But
also
like,
with
come
this-
talk to me about it later because we got to talk lab now.
Alright.
All right, folks. We are talking lab now. We are making a calcium hydroxide solution. And what I would like to know from you to start with is calcium hydroxide an ionic compound or a covalent compound? Chat with your neighbor. Oh, and I'm going to grab you guys a periodic table because we'll need one soon anyway. Is it an ionic compound or a covalent compound?
I'll play. I'll play. I like space. I need space.
So yes, I've seen the periodic table.
I haven't slept these in 20 minutes.
So this is because he has.
Actually, I haven't seen any giant mice until that one now.
I'll make it. I have like. Yeah.
Okay.
But no charges.
Nope, you don't get charges this year. Because you can know them. You can figure them out. Yes. Don't worry, we'll get there. Shh. So, look on your periodic table for calcium, please. Calcium. Hopefully, you have located calcium at number 20. Okay. And it is in which group? It's group number 2, which is the alkaline earth metals.
I forgot the name.
Alkaline earth metals. And if you had to take a guess about the charges of group 2, everyone think about it. Group 2 has a charge of? Group 2 has a charge of 17, right? No. Group 2 has a charge of? Easy. Make a guess. 2. Oh, look at that. Group 1 has a charge of? 1. These are both positive, okay? 1 is positive 1, group 2 is positive 2, and group 3 is positive 3. And then it breaks down because we're in the transition metals, okay? But when I tell you that you don't need the charges on your periodic table because it is as easy as 1, 2, 3, that's because the charges are +1, +2, +3. Yes? And we'll get into the negatives later, but it's just as easy. Now, you can write these on your periodic table, and that's fine for now, but just bear in mind when we get into writing formulas and so on and so forth, you will be given a periodic table without charges for quizzes and tests. Okay? So you need to be able to say, I can remember 1, 2, 3. Can you remember 1, 2, 3? Do I need to come up with a song for that, or are you good? 1, 2, 3, cha cha cha. 2, 3, cha cha cha. 2. No, then there's no 1. I don't know what to do. Okay. Huh? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do you guys know that song? Okay, I'll have to find it for you, but we don't have time today. So we will not do that today, but it is an alkaline earth metal. Any compound that contains a metal is what? CMPD, compound. All right, so if you see a metal, you're like, oh, ionic. It does not matter what the second part is. Okay, in this case, it happens to be, it's not just a plain old non-metal, it is a polyatomic ion. Okay, and that's because our calcium has 2+ charge, and our O attached to an H has a negative charge. Okay, the whole thing. So it is not covalent, it is ionic because it is made of a metal ion and a polyatomic ion. And anytime you see metal, you know it is ionic. Now, this is a positive ion. What do we call that? That is a cation. If you cannot remember that, you can remember that cats have pause, therefore cations are positive. Negative ions are called anion. So this is a positive ion, this is a negative ion. Question, yes? No, you're good? Okay. So we have a cation and an anion. When they come, yes? I have no idea. What kind of structure is formed when we put these ions together? What kind of structure do we get? Crystal lattice. Okay, and it's going to be small positive, big negative. Small positive, big negative. Big negative, small positive. Big negative, small positive. Why are the positives smaller than the negatives? Cations are smaller. The anions are bigger. Okay. And here's where we do a little review of atomic structure. We're not going to do this with calcium and hydroxide because it's too complicated. All right, we're going to use some tiny little atoms. We are going to use a lithium atom and a fluorine atom. Now, lithium on our periodic table has the number 3 at the top, and fluorine has the number 9 at the top. What are those numbers called? That is called the atomic number. And what does it tell you? It tells you the number of protons, and it tells you the number of electrons in a neutral atom. Do you remember that? Protons and electrons have to be equal because the atom is neutral. You must have the same number of positives as negatives. So the lithium atom has how many protons? Lithium has 3 protons. And it also has how many electrons? 3 electrons. Now, fluorine has 9 protons, and it has 9 electrons. So you can see the number of positives and negatives are the same. So the whole thing will be neutral. Okay, let's draw a Bohr model. We are going to ignore the neutrons for now. What goes in the center of the Bohr model? Protons. Okay, so for lithium, we are going to have 3 protons. And then what do we call these things that go around? We call those electron shells. Yes, you can also call them energy levels. Okay, that is a shell. How many electrons maximum in the first shell? 2 electrons maximum in the first shell. So let's put in our 2 electrons, and if you've drawn them separately in the past, I'm going to get you to draw them together. Okay, we'll find out the reason for that later on. That's our first 2 electrons, but we need 3 electrons. First shell is full, so we need to go to the second shell and put in our 3rd electron. I'm going to put it in at the top. How many electrons max on the second shell? 8. Okay. Now, over here we have 9 protons. So I'm just going to write 9 plus in the center. And in our first shell, we're going to have 1, 2 electrons. And then we need 7 more. We're not just going to draw them on randomly. We're going to start at the top and draw 1, And then we're going to go clockwise around. We're going to go 1, and then we're going to go 2. And then the third one's going to go at the bottom. And then the fourth one's going to go at the side. That puts those electrons as far from one another as possible. Why do they want to be as far from one another as possible? What does negative do to negative? Repels. So, do electrons want to be close to each other? Not if they can help it. So the first 4 electrons on shell number 2 go into a little room at the top, a little room on the side, a little room on the bottom, and then another room on the other side. Yes? Now, we have so far 6 electrons. We need 3 more. Now we pair them up because there's only 4 little rooms. So that's going to be, we have 6, 7, 8, 9 electrons. Now, do you remember the term valence shell? What is a valence shell? What? It's the outer shell. It is the outermost occupied shell. Now, I say occupied because there are more shells outside of the ones that we have drawn, but they don't have any electrons in them. So they are unoccupied, and we don't bother drawing them. Okay? What do you know about a full valence shell? Sorry? Why? Full valence shells are very stable. Now, another way of saying stable is to say it has a low potential energy. Are you guys okay with PE for potential energy? Is that something you've seen before? No. Okay. Potential energy. Now let's talk about what nature likes. Here's a pen. It's got some potential energy. Now it has a different amount of potential energy. Where is the potential energy high? Up here, and here the potential energy is low. Is this stable or unstable? Unstable, what is this? Stable. Nature tends to go from high potential energy to low potential energy, from unstable to stable. High potential energy to low potential energy. Unstable to stable. So nature's going to make it happen. Yes? If I have a magnet and I put it near this little metal clip, where is it more stable? It's more stable with the magnet than, like, as long as it's near it, it wants to be. Like if I let it go, it's like, oh, please attach me to the magnet. Yes? It is more stable here than it is here. Yeah? But then there's two opposing forces, of course, I've got force of gravity as well, okay? But basically, you want electrons to be as happy as possible, as stable as possible. Are these electrons stable or unstable? Is this system here stable or unstable? Remember, a full valence shell is very stable. Are we stable or unstable? Unstable, because this electron, we would need to either fill that up with another 7 electrons or get rid of that 1 electron. We have an empty spot here, and we would either need to put an extra electron in there or get rid of all 7. What seems like the most easy way to deal with this problem? Yeah, we're going to add 1, and where's it going to come from? It's going to come from the lithium. Yeah? So what we end up with then is this is Li neutral, this is fluorine neutral, and it's going to become, we have 3 plus, and now we just have 2 electrons, and the outer shell is now empty. And because it is an ion, we will put brackets around it, and we will put its charge. What is the charge of this ion? It lost an electron. So it's going to be, it lost 1 electron.
Oh, it's impossible. Okay, 1.
If you lose 1 electron, that's like subtracting -1. So it's going to be plus 1. Yeah? I thought you said 4. I don't know. I just can't hear. That's all. Never mind me. Okay, so just plus 1. But we normally don't write plus 1. We just write plus. If there's a number, we'll write, okay, so plus means plus 1.
I know.
Okay?
What before that? What are we going from to plus 1?
Huh?
What is it going from to what?
It's going from 0. So this is lithium
now I got it.
plus. This is lithium 0. Now, why is it 0? It's because we have 3 positives and we have 1, 2, 3 electrons, which is negative. So there's 3 positives, 3 negatives. That makes it neutral. Now, our fluorine, we still have 9 protons in the center. And we have 1, 2 electrons there. And we have 1, 2, 3, 4, 5, 6, 7. The only reason I'm not doing them in a circle is because I know this is now going to be full, right? How many electrons do we have? We now have 10 electrons, but we still have 9 protons. So what is the charge of our fluorine? Fluorine is now negative. We've got 1 more negative than we do positive. Okay, so this is F minus. Now, what do you notice about the size compared to each other? The cation, which is positive, is smaller because it lost its valence shell, right? Like its valence shell is empty. And what do we notice about our anion? The anion is bigger. Why is it bigger? Because it's full and you have extra electrons. What do electrons do to one another? They repel. Yes? The extra electron causes more repulsion. Therefore, larger. Is good? Okay. Now, here we go. Do-do-do-do. Okay. So that was a long way of going around to say that the cations are smaller and the anions are bigger. Now, this is a crystal lattice. Do I want to draw this every single time I want to draw a crystal lattice? The answer is no, because I'm going to be drawing a lot of crystal lattices. So what I'm going to do is I'm going to say, here is my crystal lattice. That's going to be our crystal lattice. Are you okay with that? I've made it a lot smaller. I've taken the box and I've turned it into a little square. Yep. Okay, so that's a crystal lattice. That way we don't have to draw this whole thing every single time. The other reason we don't want to draw it every single time is because in our lab, what form was the calcium hydroxide in when you got it? You got it in that little beaker? What form was it in? It was a solid. What kind of solid? Was it a cube of solid? It was a powdered solid. And you can think of a powder as being many mini crystal lattices. Many, many crystal lattices. So we took our calcium hydroxide, solid, and we put it into a beaker of water. Here it goes. No. It'll be due on Wednesday, same day as your quiz. But you should actually be trying to finish it tonight. And then there probably will only be one question left to do that I don't have time to get through today. Yes? Okay. Now, do you remember? It's a powder. So what do we have? We have little powder. And what are the powder? They are little mini crystal lattices. Yes? What did it look like? Could you please describe this mixture? It was white. What else? Was it clear? No, what would you say about it? It was, I'm going to be even easier than translucent. I'm going to call it cloudy.
Okay.
Okay? It's cloudy. Now, why is it cloudy? If we take some light, if we take a flashlight, there's our little flashlight, and we shine the light in there, some of the light will make it through, but if it hits a little crystal lattice, what will it do? It gets scattered. Woo. The mini crystal lattices are big enough that they will scatter the light. Can I just call them mini CLs? Crystal lattice, CL. The mini crystal lattices are big enough that when light hits them, it bounces off.
Okay.
And scatters. Therefore, it is cloudy. Is good? Okay. So it's white and it's cloudy. What type of mixture is it? Yes. It is a heterogeneous mixture. Specifically, it is there's a word. We have solid particles suspended in the liquid. They're literally just floating around in there. So what could we call this type of mixture? A suspension. Because it has solid suspended in the liquid. Yes? And suspensions will always be cloudy. And enough doesn't have a T at the end. I don't know what's wrong with me. There we go.
No.
Enough? Yes. So are we good with this? Suspension? Now, we stirred it, we heated it. What happened when we stirred and heated it? Now I'm going to go back to drawing our crystal lattice again. I'm going to draw only one because it's too much trouble to draw more than one, and I'm going to draw it pretty small. What happens to our little crystal lattice as time goes on? Does it stay like this? What was the point of heating and stirring? Each of these little guys separates and comes off. Okay? In other words, what is this process known as? This is known as dissolving. Okay? And what we end up getting with that is we end up getting these are free-floating ions. However, is this a true representation of the size of these ions? No, these are way too what? Big. So what they're really going to look like is we're going to take our positive ion and we're going to make it a little black dot, and we're going to take our negative ion and we're going to make it a little red dot. And what do we have in our beaker now? Instead of having these great big glonking positives and negatives, we're going to show them as just like little tiny black dots and little tiny red dots. Yes? But what else is in there? Is that it? Is that what it looked like? Did we still have some solid? Oh my God. Once we had heated it and stirred it, did we still have solid? Yes, we did. So we still have little mini crystal lattices. Do, 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 do. Yes? But we have fewer of them now. Mini. What does CL stand for? Crystal lattice. So we have little mini crystal lattices and we have ions. Okay? So we heat and we stir and we get that. Yes? What did we do with it next? You heated it, you stirred it, you waited, and then what? You filtered it. Yes. Okay, so let's say that these little guys represent individual ions. Okay? So maybe this ion was here, and this ion was here, and now it is dissolved into the water, and this one is dissolved into the water. So I still have a little mini crystal lattice, which I'm not going to hold because I don't have enough hands, and I've got these free-floating ions, yes? And I'm going to take the whole solution and I'm going to pour it through some filter paper, yes? Now, the filter paper has little holes in it. Okay, here's the hole in the filter paper. What happens with the ions? They go right through because they're small enough. What happens to my little mini crystal lattices? They don't go through because they're too big to fit through the holes in the filter paper. Okay? So the ions are tiny. They are small enough to fit through the holes in the filter paper. The mini crystal lattices are too big to fit through the filter paper. So we're going to now pour this through the funnel. There's our filter paper. I assume you guys are talking chemistry, yes? Okay, cool. All right, so we've put it through and the little mini crystal lattices get stuck, right? But the ions and water is also a teeny tiny molecule. Water and the ions drip out the bottom. Do you know what we call this solid on the filter paper? That is our residue, yes. The filtered solution, what's that called? That is called the filtrate. So we have our residue and we have our filtrate. So now, I don't want to redraw this like way down there, so I'm going to draw it over here, okay? Filtrate. And what's going to happen if we shine our light through this part? It goes straight through. Okay? The ions are too small to scatter the light. And that means if it's too small to scatter the light, therefore it's going to be cloudy or clear? Clear. Now, in this case, it happened to be clear and colorless. Thus, it looked like water. Yes? And yeah, but you could have a colored solution, which is also clear. You can have something that's clear and blue. You can have clear and red. Your Coca-Cola is clear and brown. It's a very dark brown. It actually doesn't scatter the light, though. It absorbs light because of its color, but it doesn't scatter it, so it's not actually cloudy. And if you make it thin enough, you'll notice that light does go straight through it, and you won't see any cloudiness. It is see-through as long as you get it like to a fine enough layer, and it won't look cloudy at all. Okay? The only thing, two things we've not talked about yet, one of them is our saturated solution. Let's see if I've got it on here. No, I don't. That's exciting. What? Oh, here. It's okay. It's okay. There. Sorry. I'm just looking for things. Does everybody have a copy of the vocabulary list for this unit?
Yeah.
Anyone need a copy of the vocab list for this unit?
Oh,
Yes.
Who
Who else needs a copy?
Yes. Oh, you do. I can feel
Okay. And yes, I'll make a copy of these notes available for you for tomorrow. Okay, the stuff we've been writing.
Can you go off? I want to see the top of the. Yeah. Relationship.
We good?
Yeah.
Cool. All right, so we are going to go then to here. This is the last page of your vocabulary sheet. Okay, so make sure you've got your vocab sheet out. We're on the last page of the vocab sheet. I know that feeling though. I understand that feeling. It's like the end of the day. It's the end of a long day. I get it.
You have to hand me what I just brought in.
No,
I wrote it in cursive and it's.
no, it's okay. I can read cursive, but it's all right.
You could read this.
For our next.
We'll see. We'll see.
For our next lab, we should just chemically make an energy drink to help us.
All right. So just so you guys are clear, right on the very back page, we have a suspension versus a solution. You don't need to write any of this stuff down because we just took notes on it, but it's just reiterating that in our solution, we have individual ions, and it's clear the light does not get scattered. But the moment we get to a suspension, the light gets scattered. All right, and you can actually see these little mini clumps of solid, and the light is getting scattered off of them. And the little ions are too small to scatter light. Other things you should notice about a suspension is that the particles will settle to the bottom. Did you notice that the particles of the suspension did tend to settle a little bit, even when we were heating it? Did you notice you kind of got a little layer at the bottom? No? Yes? Okay. If you were to leave it overnight, maybe over the weekend, probably it would all settle out. Yes? Okay. Do you think if you leave salt water out that the salt is all going to settle to the bottom? Is that your experience with, like, say, the ocean, that all the salt settles to the bottom, leaving pure crystal drinkable water on the top? No. Okay? And that's because particles will not settle to the bottom in a solution. Suspension, they will not pass through the filter paper. Solution, they will pass through the paper. Now, last but not least, we have our saturated solution. Don't lose the plot here. Don't put your books away. Don't start shuffling. A saturated solution contains the maximum amount of dissolved solute. How are you going to know that you have the maximum amount? Well, maybe we start with a whole bunch of solute. And at the start, it all dissolves. Yes? So you then have a smaller pile of solute. Some of it is still dissolving. Those are the little red arrows. But some of it is going from ions back into crystal form. That's called recrystallizing. Okay? But this is unsaturated, so there's still going to be more dissolving than there is recrystallizing. finally, you will get to a point, you're stirring and stirring and stirring and stirring, and oh, there's some solute that will not dissolve. You've stirred it for like an hour now. Okay, you're not going to stir it for an hour, but you stirred it for a good long time, and some of the solute is not dissolving. That's how you know you have a saturated solution, is if you stir and no more dissolves, that is saturated. And you'll notice, what about the size of the red and the blue arrows? They are the same. It means that for every particle that dissolves, the solution is now full. Another one has to recrystallize. It's as though you're at a hotel and you're watching the outside of the hotel, and there's a huge crowd of people and they're all checking into the hotel. People check in, but then some people are done and some people check out. Yeah? But if you still have more people, they'll check in until the hotel is full. Now, once the hotel is full, you're going to have a crowd of people outside who cannot get in. And for every person who checks out, a person can go in, but the crowd of people outside will stay the same. Okay? Your homework is to complete the lab to the best of your ability, but it's not due till Wednesday because we haven't covered the last question yet. And to do those practice questions for your quiz on Wednesday. So everything's kind of like 2 days away, but do it tonight because otherwise you've got everything tomorrow night and that would suck. Okay? Hi. We can talk now. Okay.
Oh my God, this is so much